Okay, so here we're going to prove that if we have a graph G, which is a vertex set V and a set of edges E, and the size of the vertex set is bigger than or equal to 2, then there are two vertices that have the same degree. So we'll say the vertex set V is equal to V1, V2, all the way through Vn, and we have n is bigger than or equal to 2. We want to show that the degree, if we wrote this in symbolic logic, we'd say that there is an I and a j with 1 less than or equal to I, which is less than j, so they're not the same, which is less than or equal to n, so that the degree of vi is equal to the degree of vj. And this means that they have the same number of neighbors, or they're connected to the same number of vertices of other vertices. They're adjacent to the same number of other vertices. We're going to prove this. This is maybe a little bit of a surprising fact. Something that wouldn't jump out at you. There are a couple ways to do this. As always with these, I'm gonna try to go for the sort of nicest, cleanest one, and that's going to be, or what I think is the nicest, cleanest one. By contradiction. There we go. Can I spell contradiction? Perfect. By contradiction. And so what is this saying? This is saying that there exists two that are the same. Contradiction. So our statement is there are at least two with same, it doesn't say same degree. What is the negation of this? What is the opposite of this? That they are all different. They all have different degrees. So we're going to suppose, for the sake of contradiction, that they all have different degrees. If we were to symbolize this, this would be for all I j with 1 less than or equal to I less than j less than or equal to n, the degree of vi does not equal or is not equal to the degree of vj. So they have different numbers of connections, of vertices that they're adjacent to. They have different numbers of neighbors. Trying to use the proper terminology here that you'll probably find in the textbook. Okay, so so we're going to suppose this. We suppose by way of contradiction. I'm being lazy just writing BWOC, but never hurts to actually write out by way of contradiction every time. That they all have different degrees. Well, what does this mean? This means that D1, or this means that let's I was skipping ahead a little bit. This means that dv sub I is not equal to d of v sub j. The degree of dvi is not equal to the degree of vj for all ij less than or equal to n. If they're all different, then we can say without loss of generality, d of v1 is less than or equal to, I'm sorry, not less than or equal to, it's strictly less than. D of v1 is strictly less than d of v2, which is strictly less than d of v3, all the way through is strictly less than d of vn. And without loss of generality, if you haven't encountered this before, this means that, so if they're all different, right, then there's a smallest one, there are n of these. There's a smallest one, and then a next smallest one, and then a largest one. And for the sake of simplicity, we can just relabel them, right? Suppose that that Vn had the smallest degree and V1 had the largest. Well, we would just relabel V1 as Vn and Vn as V1, etc. So relabeling, something you might see in textbooks, they would say relabeling, if necessary, we can suppose that d of v1 is less than d of v2, etc., is less than d of vn. It's supposed to be a laser tail. There we go. But what is the smallest possible number that d of v1 could be? So this is the number of connections, the number of vertices that v1 is adjacent to. Well, the fewest vertices it could be adjacent to is 0 if it's isolated, if it's not connected to any vertices. Then it would have a degree of 0. And what is the most? So we know that d of v1 is less than or equal to 0. What is the most that the highest degree that a vertex could have in a graph? Well, if there are n vertices, right, v1 through vn, then any particular one of them, like vn, could be connected to all the other n minus 1 vertices, and it would have a degree of n minus 1. That is the largest degree that it could possibly have. So we have 0 is less than or equal to d of v1, which is less than d of v2, all the way through d of vn, which is equal to n minus 1. But how many of these are there? How many of these are there? There are n of them, and these are all elements of the set 0 through n minus 1. Right? These are all, each one of these is a natural number, or an integer, if we're not considering 0 part of the natural numbers. It's an integer in 0 through n minus 1, and there are exactly n of these, right? Counting from 0 to n minus 1 is n numbers. So what does that mean? That means that the set of these degrees, d of v1, d of v2, etc., through d of vn, we know that it is a subset of the set 0 through n minus 1, and it's a subset of the same size, right? Their cardinalities are equal. So I'm just trying to write this out a little bit formally here, just so that because people are going to see this and be writing the arguments on tests. Sometimes I don't do all the details that we need, because it gets to be a really boring sort of dull video if I'm doing every tiny little thing. But we should do sort of, enough that people see, okay, you can actually justify these things when you're writing a test. Never, I've mentioned this many times, never hurts to put more details, even if you think they're unnecessary on tests, because they love, especially with first year with introductory students, to make sure that you prove every tiny little detail, no matter how obvious, because they don't believe you that you just sort of know it. When you get more advanced, it's easy to forget to do these things, but it's good to keep in mind that, well, since the set of degrees, d of v1 through d of vn, is a subset of the numbers 0 through n minus 1, and it's a subset of the same size, that means that they are equal. That it's not just that this one is a subset of 0 through n minus 1, they are the same set, they are equal. And what does this mean? What does this mean, that they are equal? Well, that means that it's not just that d of v1, we don't know that d of v1 is just bigger than or equal to 0. It has to be equal to 0. And d of vn, it's not just that it's less than or equal to n minus 1, it has to be equal to n minus 1, right? These are the same numbers as these in order, right? d of v1 is less than d of v2 all the way through d of vn. So that tells us that d of v1 is equal to 0. d of v2 is equal to 1. In general, d of v sub k is going to be equal to k minus 1. We put our dot dot dots through. I'll just keep going down. I was going across because it looks weird to go over this sort of page separating line, but I think it looks stranger if we start going across. You're not supposed to do that on tests, by the way. You get to go one across and then down generally. This isn't exactly that case, but still, I think that it's nicer to go down than up here, or off to the side. There we go. 0, 1, 1. Okay. And so here we have our contradiction. What is the contradiction? Well, because it might seem a little while back, but we decided that we were proving this by contradiction. We assumed that the graph had more than, or it had at least 2 vertices, and that all of them had different degrees. And then we found out that means that the 0 is the least, the smallest degree that a vertex can have, and minus 1 is the biggest. And so these n vertices have to have degrees 0, 1, 2, all the way through n minus 1. But this is a contradiction. This is a contradiction. And why is that? I'm going to change colors for this to really emphasize this. This means the fact that the degree of Vn, it has maximal degree n minus 1, that means that Vn, I won't do this part in that color, Vn is connected to all other vertices. Or it's we would say it's neighbors with. I'm trying to use the sort of textbook terminology here. It is neighbors with, because this again is one of the things that you find out, especially when you go to a really rigorous school like U of T, that they will actually take off a mark for stuff like this. They say connected, and it does have a different meaning in graph theory, right? Here, this is the everyday English language meaning. It's connected to the other vertices. A connected graph is a particular thing in graph theory. So we're saying it's neighbors with, or whatever the prof in your course wants you to use, or it's adjacent to all other vertices. And so, because it has maximal degree, right? It's degree is n minus 1, that means it has n minus 1 neighbors, and there are n minus 1 other vertices that it could be neighbors with, that it could be adjacent to. But d of v1, the degree of this one has to be equal to 0. So that means that v1 has no neighbors. It is a lonely vertex of the graph. It doesn't have edges connecting it to any other vertices. And lonely, of course, is not the term. Although in math, yeah, every once in a while you do come across a concept where they use a sort of very seemingly non-mathematical term to describe something. Say a lonely set is this kind of set, or like a faithful group action or something like this. But the idea is that this one has no neighbors. If its degree is 0, it is not adjacent to any other vertices. But this one is supposed to be adjacent to all other vertices, and these are incompatible, right? This is incompatible, because this one is saying that Vn is neighbors with V1, and this including every other vertex, and this one is saying that V1 has no neighbors. So that is impossible, and that is our contradiction. And so therefore we can conclude that because we assumed the opposite of this, we assumed that it was not true that there was at least one pair of vertices that had the same degree. So that's true and that's saying that for all vertices, they must have different degree for all pairs of vertices, which are different. So vi is not equal to vj. And by the way, I did the I less than j arbitrarily. It could have been j less than I. This is just to say that they're different, right? Again, the whole idea is that this is just telling us that vi is not equal to vj. And so assuming that they all had different degrees led us to a contradiction. And that means that it must have been false. That assumption must have been false. And therefore, its negation that there exists at least one pair of vertices, vi and vj, that have the same degree, that must be true. And so that completes our proof.